Welcome to the next week of the course Metal Additive Manufacturing. We have till now discussed multiple technologies and the processes which are used for additive manufacturing of the metals. Also we have discussed some physics like solidification that happens when we try to develop the product or the component using additive manufacturing, then additive manufacturing of metal matrix composites, the in situ and other controls. In this lecture, I would like to discuss reverse engineering used in metal additive manufacturing, and the contents of the lecture would go like this. I will talk about what is reverse engineering, what is the process to conduct reverse engineering. With reverse engineering industries which have majorly taken the acumen to develop the products using additive manufacturing, then what is the purpose of reverse engineering specifically, methodologies and stages in reverse engineering, then reverse engineering for additive manufacturing specifically, then an examples would be taken to elaborate the things which I explained, then different kinds of scanners or the reverse engineering equipment that are in use. What is reverse engineering? Reverse engineering extracts design blueprints from man-made objects. Reverse engineering could be applied to any of the processes, any of the products that you would like to replicate. For example, if you have a chair with you, you would like the carpenter to produce a similar chair. He will come, he will measure the dimensions using the measuring tape, he will see what are the different shapes, he will try to replicate the same components and same parts of the chair and try to produce it for you. If I am having a blazer and I can't visit my tailor once again, I send my blazer to the tailor and tell him, please make a replicate of this. What he will do, he will take all the dimensions, he will measure everything, try to see what are the different alliances and see, and will try to produce that. This is reverse engineering when we are trying to produce a copy of an existing product or we are trying to study a product. For example, the tailor would also like to teach his new students how to stitch a blazer. What he will do, either he could start the forward process, he can say, okay, this is the cloth, these are the cuts that you make, these are the shapes and these are the stitching processes. Another way is he can give them a stitched coat which is not in use. He can tell, okay, you please try to unstitch it and try to see what are the various curves, what are the various points there that you need to understand when you try to dismantle or unstitch a coat. So that is reverse engineering. So it is blueprints from the man-made objects. The idea undoubtedly dates back to the industrial revolution itself before computers or current technologies. Now software reverse engineering is also one of the processes that is the talk of the town, because software is also replicated and the similar kind of the firmware in the mobile phones also we receive. So it is analogous to scientific research where a scientist tries to decode the atom or the mind. Reverse engineering investigates created artifacts while scientific inquiry investigates natural phenomena. When we miss some knowledge, some idea, some design philosophy, reverse engineering is used to understand how the product was developed, what could have been the processes in developing this product. Some people won't disclose their information, sometimes the information is lost or deleted. So reverse engineering has certain purposes that we will discuss when we go through this lecture. Reverse engineering traditionally included dismantling shrink wrapped objects to learn their design. So how the object is designed, to replicate that, to understand what are the different components, what are the parts of the assembly, what are the various operations that have been carried out to produce these objects, what will be the steps in assembly, all these things are taken care of when we are trying to learn the design of the object. Now secrets were employed to build similar or better products. Reverse engineering was formerly a popular hobby, even it wasn't called that. Now two processes are there to learn something or to build something. Obviously the forward and reverse engineering. In the forward, first we do analysis, we try to put in the mechanical engineering. If we're trying to produce a product, we try to first produce the idea, we try to generate the idea, then we try to design it. This design could be in the form of CAD, then we try to implement that. There are three simple steps: analysis, design, implementation. This is forward engineering what you do, right? What is engineering? Engineering is application of the scientific knowledge that you have. Scientist tries to develop something novel, engineering tries to apply that information that scientists have generated. Now, implementation, that is the product that is there, recovery from that, and try to recover design from that implementation, then try to analyze what could have been the idea. This is reverse engineering. So, there is a clear delineation between how do we go about and understand what is reverse engineering. Now, a reverse engineering process typically involves these 4 steps. They are the multiple steps which are part of it. Each of these steps, for example, digitization in itself could have 10 tasks in it, but digitization of the objects, that is the data capturing using the machines such as scanners, coordinate measuring machine, etc., is the step number 1. The example which I quoted, that the tailor would take the tape and try to measure the dimensions of the cloth or the blazer that is already built, or the carpenter will also take the inch tape and try to measure the dimensions of the chair. So, this is data capturing. He will note the dimensions on a paper, he will try to make a small drawing, small cuts, he will just mark the important points where the things are to be properly set. This is data capturing. This is a very trivial example that I have given. If I am trying to reverse engineer a product, for example, my complete laptop, I need to understand what are the components of the laptop, before the components, different assemblies of those, what are different dimensions. It could be, or I would say in general, if I need to just produce the outer shape of the laptop, this is an object, how could this be done? The scanners try to produce the 3D model of this. The 3D scanners are there, which we will discuss. Then these 3D models, when we try to scan through, these have certain noises, certain missing points, how to treat them, that is known as data cleaning, that also takes place. Then we try to build a bridge of that, this RE bridge, and we try to then develop a CAD model. Now, processing of the measured data implies the data that is scanned, there would be multiple replicates of the model or of the data that is scanned. For example, if this laptop is to be scanned using a 3D scanner, it would be scanned maybe 20 times. It would be kept on a plate that would be rotating, here the laptop would be kept. So, the scanner light would try to emit the laser or also try to reflect it back to the receiver, and the cloud data is generated. This does not happen in one go. These rotations might be 5, might be 20 or so. So, at each rotation we are having some information of the product, and this information is to be collected together into a single RE bridge or single model, CAD model, that we need to have finally as our reverse engineered soft prototype. Now, creation of the CAD model would be the next step. Then the prototype development. Prototype development is nothing but we try to have a STL file from here and try to 3D print it using multiple processes that we have learned in the previous lectures. Now, again a typical example. This is a wooden pattern of an impeller. When we try to reverse engineer it, what we get is, we get the cloud data. The cloud data, you can see the dots are only there. The dots are the points which have been captured using the 3D scanner. These dots are then converted into mesh. That part also we will discuss. After 2-3 iterations or 2-3 steps in between here, so we get the CAD model. The CAD model has the complete shape of the original pattern that we have, right? Now, this CAD model, definitely it is 3D printed here. It could be 3D printed in polymer, in metal, in whatever material we require. In this case, this is a complete model. There could be certain ways when we try to scan. For example, this is a completely symmetrical about this axis. So what we can do, we only need this angle, right? And we need to understand this thickness of the fins of the impeller. So we can even scan half of the object, for example, only half of the object, right? Or I can even scan only small portion such as this portion only. And using the array command in my software, I can produce the array of these and try to have my complete object. It depends upon the resources that you have. Reverse engineering, any of the processes that you are trying to implement, the time is one of the factors, and time is proportional to the money that is incurred in it. So to minimize the time of reverse engineering and to get the best information, the quality of the data that you have has to be legitimate to have the CAD model proper. So there are multiple ways to deal with it. Now the scanning could be conducted using two types of the scanners. One is the contact type, another is the non-contact type scanners. Contact type scanners, obviously using a measuring tape, we have to completely touch and have the measurement. This is the contact type of the measurement. Non-contact type would be the scanners if they get the data digitally without having the actual contact with the object that is being scanned. In the contact type scanners, in mechanical, we have coordinate measuring machine based scanners, which are the major contact type scanner. For example, there is a probe here, there is a sapphire tip here, which is a soft tip. It keeps on having the data at certain points, 1, 2, 3, 4, 5, 6, 7. At this point, we can have more closer points, 8, 9, 10, 11, 12, 13, 14. All these points would be gotten, then these points would be connected, right? Then it can have points here, right? Then this kind of the scanner would only get the information while touching the component that is under the scan. Now soft materials cannot be scanned. There are the certain limitations, because if the soft materials will be touched, for example, the food items, the bread or the cloth, the probe will just go inside or won't have the exact information. It is a comparatively slow process, right? Because mechanically the component has to move from one place to another, and this takes its time. Now there are the alternatives for these non-contact scanners, which uses lasers, optics, and CCD sensors to capture the data points. Now one of the drawbacks in the non-contact scanners would be it cannot scan these shiny surfaces, because the light, when it falls on the object, it is reflected back. The shiny objects will obviously have some reflection index, so the light won't be giving the exact information. Similarly, the black objects might absorb the light, right? So shiny surfaces or black surfaces cannot be scanned with this. For that, we have a pre-treatment before scanning that is there, we try to do. So the lasers, optics, then charged coupled devices, that is CCD, this all helps us to get the data. Similarly, surfaces which are parallel to the light axis cannot be scanned accurately using the non-contact scanners. Now, if I try to classify the hardware of the reverse engineering, majorly we have the coordinate measuring machine systems, which are the portable CMM systems, which are also known as the ARM kind of the coordinate measuring systems. So this is in an ARM, so it works on the polar coordinates. So wherever we touch it, it could have a touch kind of the system. You can see a probe is there. Also, a light could also be there that could help us to understand the system. It works in both the contact and non-contact systems. Now, laser trackers are also there. Laser trackers are generally used in civil engineering to have the measurement of the large distances. Total stations are also there. This is a total station that tries to have the information around this 360 degree in as 1 degree of rotation. Another degree of freedom is this direction, right? So also this could also be rotated. So digital photogrammetry is also one of the processes that uses different hardwares. The contact methods. Now use sensing devices with mechanical arms, coordinate measuring machine, and CNC machine to digitize a surface. So data collection techniques are of multiple types. Majorly two of them are point-to-point sensing and analog sensing. Point-to-point sensing is when I manually try to scan my object from one point to other. Like these are the points that my scanner is trying to capture here. Point to point, it is manually being moved from one point to another using a joystick that is an attachment to the coordinate measuring machine. So, in the contact kind of the sensors. So, these point to point sensing with touch trigger probes installed on CMM or articulated mechanical arm to gather coordinate points of a surface. So, CMM provides more accurate measurement data compared to the articulated arm, but I would say complex shapes are difficult to be scanned using this. Next is the analog sensing. Analog sensing is an automated system in which the sensing happens through CMM or CNC machine. Now, in analog sensing, the scanning probe provides a continuous deflection output that can be combined with machine position to derive the location of the surface. The scanning speed in analog sensing is up to 3 times faster than point-to-point sensing because this is automated. In this, we just make the CMM system to understand, okay, you have to start scanning from here. It will keep on scanning the points. When it reaches this area, it will understand it cannot go above. So, it will start taking points this direction. Then it won't find any area here, any object in front of it. It will start scanning in this direction. But this is an automated system. Automated, that is called, we call it analogous. Now, point processing system that is used to import the point cloud data, that reduces the noise in the data collected, that reduces the number of points as well, because manually we can definitely select which points are important. For example, if this is this big length, I have taken 2 points here. I would just need one more point to understand this is the length. So, this is only in 3 points we will get the whole information of the surface, right? And definitely these coordinates would be marked, it might be 10 centimeters or so. So, we took it in the first centimeter, we took it in the last centimeter, that is the 10th one. Only 3 dimensions gave me the dimensions or the length of this. If 2 dimensions, 2 points could even give. In the analog system, if I have made it to have the resolution or the point distance as 1 mm or maybe 2 mm, so it will take number of points here. So, this becomes a slower system at certain points if the dimensions are longer, but if the shape is complex, something like this, in this the analog system would move faster. It will take its points by itself, right? Now, these tasks of measurement using CMM are performed using a range of predefined filters already. Multiple scans are sometimes needed to ensure that all the required points are scanned, and a wide range of commercial softwares are required sometimes to clean the data as well. The output is a clean, merged point cloud data set in most convenient format. Now, point-to-point sensing equipment, in this we have the CNC coordinate measuring machine. Just to show you, I have put the Zenith 3 CNC CMM as an example. Other than that, we have the SP25M scanning probes from Renishaw. You can say different kinds of probes are there for the deep to reach surfaces. This kind of probe could be used. These are the probes for the surfaces which are even less deeper. There is a probe that has 1, 2, 3, 1 on the other side, 4 and 5 different directions of the points or end points that it has. There are different kinds of probes that could be used. Now, this is the Roland DGA Corporate MDX20 scanning and milling machine, which is using Roland Activate piezo sensor for 3D scanning. So, this is also a kind of a CMM machine. Now, advantages of the contact mode of the scanning is it has high accuracy because it is all contact. We know where the points are there, and the points are recorded in the Cartesian coordinate system in general. So, we exactly know what information, what data point is there. Data cleaning is very minimal here. Then the costs are low for these scanners because these are the contact kind of scanners. We do not have much sophisticated softwares in between. The ability to measure the deep slots and pockets is possible using this. Sometimes the light doesn't go very deep. So, these deep slots are taken using the longer probes that we have. Then insensitivity to color or transparency or so. Transparent objects, the shiny objects, black objects are difficult to be scanned using the non-contact type of the scanner because the light is the source of the scanning. Now, non-contact methods include two-dimensional cross-section images and point-to-point clouds are captured projecting energy sources. Energy sources could be light, sound, magnetic field or an object. Then either the transmitted or the reflected energy is observed. It is either transmitted through the object or it is reflected back. Geometrical data are calculated by using triangulation, time of flight, wave interference information and image processing algorithms. So, triangulation method, when the light falls to an object or on an object, it returns back, this makes a triangle. This angle of the triangle for each point that it gives me the data that it is recorded. Now, this is triangulation method when the light is reflected back. It could also be transmitted through, for example, this is a grid that we have, light is made to transmit through this object, it will fall on the object, right. So, this grid as a two dimension would give me shape at this point, a second point and third point and so I can even get the information in this way. So, this is known as shape from stereo method. Right, this method. Now, classification of the non-contact reverse engineering hardware are based on the sensor technologies or data acquisition techniques employed. The non-contact methods are of multiple types. We have reflective type of technology and transmittive technology. Transmittive technology is the CT and MRI majorly used in the medical devices. We have computer tomography and magnetic resonance images. These are the transmissive technologies. In reflective, when the light is reflected back, different methods which I just mentioned here, the triangulation, time of flight is when the light goes and it comes back. So, this is time t of going and coming back. So, t by 2 is the time when light comes back to a farther object, for example, to farther dimension, this time would be, for this time is t1, this time is t2, that is larger, right. Here t2 is larger than t1 and the time of flight is t1 or t2, the dimension could be taken by considering that time t by 2, t1 by 2 or t2 by 2, right. Wave interference information, image processing, different kinds of methods are there. So, those methods are the non-optical and the optical methods. The non-optical method, sonar, microwave radar technologies which are used. Then in optical method, passive measurement or active measurement could be taken. In the passive measurement, I just mentioned shape from stereo, shape from shading, shape from focus, shape from motion. So, these are not a direct measurement. As I told you, the light just goes and tries to put the shape through a two-dimensional area that we have. Now, active methods are coherent laser radar, time of flight, Moire effects, structured light and triangulation. Generally, there is no physical contact. That is one of the advantages of the non-contact methods of the reverse engineering. Now, fast digitization of the substantial volumes is there, good accuracy and resolution for common applications is there, ability to detect colors is sometimes also there. Now, there are different kinds of the scanners available like Faro gauge arm that can also let you know what are different colors. If I am trying to scan this object, it can give me, okay, this is one object, this is the second component of that. So, it can give it in a different color. So, these different colors could be detected here. The ability to scan highly detailed object, because the scanning resolution in the non-contact scanners could go up to microns. So, we can have more detailed of the object that we are trying to scan. So, intricate shapes could also be scanned easily. So, where the ability to scan highly detailed objects is there when mechanical touch probes may be too large to accomplish this task. So, when reverse engineering a mechanical product, you start by examining its measurements and qualities, which means during the analysis, during the collection of the data, you measure width, length, height of the product's components, because these dimensions affect the performance. Sometimes we need to employ the 3D scanning for these measurements. We can automatically log correct product characteristics from 3D scanners into the databases. Now CMM, CT, laser, and structured light digitizers are 3D scanning technologies, which is already mentioned. Recording the relevant information, one can build a CAD designs and analysis for the development, which is already discussed. These CAD drawings are digital 2-dimensional and 3-dimensional representative of the product design, the CAD drawings. The digital models reveal design intent and guide reverse engineering. Obsolescence of old computer parts often require reverse engineering. Old computer parts sometimes are to be reverse engineered to understand what are the components of this, and because of these are obsolete, these are out of the date, these are to be updated. So to understand them, reverse engineering is required. Technicians reverse engineer a printed circuit board by identifying its components. Reverse engineering team will photograph the board from the front and rear before disassembly. This is regarding PCB only. Now, the team measures capacitors, resistors as they remove them. This helps the team to grasp the design engineering. This is a PCB, printed circuit board design again. It also shows how the PCB's components interact together. First, they lay out a fresh board, then install the components in the same order. Once constructed, the board is tested for functionality. The team will digitize results for future study. Just to take an example, the printed circuit boards or the motherboards of the computers, when we try to see them, so how are the components being arranged here, and what do we try to do to have the more space to install some more small components there. This is required when we try to reverse engineer something. Now, legacy purpose of reverse engineering is specifically we have a legacy for the part replacement. We have parts service or repair, then we have failure analysis of the components, improvement in the existing components, try to understand which are the specifically weaker points or weaker components which are there, which can be replaced or improvement could be made, diagnostics and problem solving, legacy of the part replacement. Part replacement, when I say the legacy part replacement requires inspecting, replicating parts of larger machinery to keep them running. Now, a factory's big engine compartments keeps the conveyor systems functioning through each shift. Sometimes each machine part needs to be replaced, or sometimes the small machine parts is to be replaced. So if the machine is old, some parts may not be longer to be made from the original equipment manufacturer. So this is out of the business. So metal additive manufacturing helps us to develop the components which are out of the production from the original equipment manufacturer, and we try to replicate them. So the factory could buy a new conveyor system, but replacing the defective element is preferable. So small, this is the replicate of the components which are produced from the polymer, just to have a test of the shape of the component, because this is not much expensive. For example, this component, if developed through the polymer additive manufacturing, it could have been costed maybe 1,000 rupees, right? But we try to test the shape, exactly the dimensions, then we go to the metal part and we try to produce the final component, which is reverse engineered. So this is an existing component, this is the new component that is being built. This is how we go about. Now, the topology optimization could also now come into play when we try to reduce the volume of this component. For example, this inner volume might not be even required. This volume might not be required, only a small connection or mesh could only help. So those small updates and optimizations could definitely help here. The reverse engineering uses a 3D scanner to reproduce a damaged parts design. Depending on the component size and complexity, reverse engineering could cost more than a newer model sometimes. So this is a component that is defective now. This is a reverse engineered part that is produced. So once we have produced a digital duplicate of the original design and replicated the part, we can reuse it. Reverse engineering helps us to replicate parts that work in our mechanical setups, even if the original producers are gone. Now next is the parts service or repair. If you need to fix or service a legacy part or a component that the original equipment manufacturers no longer supports. It helps to know how the product works. So with this information, the repair can be done correctly. At least to understand what are different parts of the machine, we need to dismantle the machine and understand the original make, how was it developed. So this is also reverse engineering. For example, if there is no design document, a company may use reverse engineering to make them. So with the information that one gets from reverse engineering, he or she can figure out which parts are needed to be changed or to be fixed, or which is where the problem is. It can also help to fix something by giving us a better idea of how to get to or to remove or to replace a component. Now next, a failure analysis is also one of the purposes of reverse engineering. Failure analysis is the way to figure out what went wrong with something. If a machine breaks down, you might have to take it apart or look at the design files to figure out what went wrong. So once you know this, you fix this. So nothing can be manufactured unless it is measured, nothing can be fixed unless it is understood, nothing can be retrofitted unless it is rectified. So first we need to have the correct measurement, correct understanding. So that means if we know this, if we know the dimensions, then only we can fix this. So reverse engineering only helps us to understand what dimensions, what shapes, what different intricate points, or what are the weaker points. For example, the locks, this is the mouse, right? The weaker point here would be this lock of the mouse that helps me to get the cover, back cover engaged. So to understand what are the weaker points, so that helps us to gain the information that how the product could work again. So by using reverse engineering to look at the product or the broken parts or the bad designs, we can understand what new improvement could be made. Looking at the digital design files made with reverse engineering, that can help us to find flaws in a piece of equipment and figure out how to fix it. Now parts improvement, which we just discussed, is also one of the purposes. Parts can also be made better with help of reverse engineering. So after figuring out what part broke and why did it broke, what were the weaker points, one might need to replace it, and taking into account the weaker point could be improved here. So it might be a time to upgrade the component now. So if you can't find a replacement or an alternative part, you can get the part reverse engineered to make a copy of the original design. Then we can modify the design to make it work better. If the machine needs its joints or welds to be stronger, then broken parts will be measured and redesigned with the thicker metals or stronger joints. Now through reverse engineering, you can figure out what needs to stay same and what could be changed. Now diagnostics is also one of the major purposes, diagnostics and problem solving. Reverse engineering can also be used to figure out what is wrong with an industrial process and how to fix it. In a factory setting, if a function is broken or not working, it can sometimes slow down the flow of the work. So the flow of the work has to be continued, has to be keep on going, right? So that is why reverse engineering helps us to have a clear diagnostics and solution to the problem that sometimes come. Now in a manufacturing system, identifying the problem causing element is hard. Through reverse engineering, by knowing the working, you can easily identify the faulty element. Also, we can design a new component. In an industry, reverse engineering is used to design a new component. The design of a new component part comes from an existing physical real part. Then we can have a reproduction of an existing component. Reverse engineering allows you to reproduce components with no data, designs and details. Recovery of a damaged or broken component. These are the actual applications that happens in the industry. A reconstructed CAD model would precisely compare damaged or worn out parts with the true part surface. Now reverse engineering methodology, it has certain steps: the input, data capture, scan data format, data processing, compatible softwares which helps us to produce them, produce the CAD model, then end applications. Compatible software would help us to have the proper solid 3D CAD model. Then end applications would be having a 3D printed object in this case. Now, the input would be the component or the object that is being reverse engineered, that is under the study. So, this could be a damaged part, right, then or a worn out area of some part, right, or maybe a full machine for which we are trying to understand how the machine was built. Now, next is data capture. For data capture, we have different scanners, like we have coordinate measuring machine, we have the laser scanner, we have optical scanner, right, again the transmittive and reflective kind of systems, and we have definitely MRI, CT, and the shapes form, stereo, and so on. The scan data format, in generally the format for 3D printing is STL format, in which we get the layer by layer component. For example, this is a component. So, layer by layer the component will build, that is majorly developed using the STL file, right. So, this is the format, because I am talking only about additive manufacturing here. So, STL format is there. Data processing is the most important part. Data processing is cleaning of the data. In the next part of this lecture, I will have a laboratory demonstration in which the 3D scanning would be demonstrated. We will try to explain the components of one of the 3D scanners, and also we will try to say how the cleaning of the data happens there. So, data processing needs the noise reduction. When I say noise, there are extra or unwanted points which are there in the unwanted clouds are also built. So, these are also reduced, or these are sometimes segmented. Noise reduction is one part. Then we generate in the processing the boundary curves, generation of boundaries. Once the data noise is reduced, these are still the points. From these points, we try to generate the boundaries of the major components. From these major components, these are the complete boundaries. From the major components, we try to generate the surfaces. Now, compatible softwares are always required. There could be softwares, for example, the GeoMagic, just different versions of it, then Pro-E, ANSYS, these are ANSYS is a analysis software, then COMSOL. Sometimes if some scientific input is required, we need to conduct small simulation over it, try to understand the failure, try to understand the behavior of the object against specific parameter, for example, heat or strength. These things could be taken care of. Then we have the end applications. End applications, in this case, we have a CAD system, and we have the CAM system, or we have the computer aided engineering system. So, we have our 3D printing, right. So, we have the physical object here. It could be physical object, it could be the documents. Sometimes the physical object is not required. The purpose of reverse engineering is just to understand the process and keep the record with us, so that in future whenever required, that could be used to develop the physical objects or to understand the failure or the broken part that if it is there. So, then documentation. So, these are the outputs here. So, this is reverse engineering methodology majorly. So, with this I will close the first part of my lecture on reverse engineering in a metal additive manufacturing. I will continue this lecture on reverse engineering, and I will discuss the steps, the details of the steps, and the laboratory demonstrations in the next lectures. Thank you.